So this is the row structure of PBXT, which consists of a number of records. And starting at the top, this is the row index file, where the row ID is a direct index into that file where I find a pointer to the most recent version of this row. And then, as I mentioned, each row itself points to the version that came before it, and you have a list of records, so a row consists of a list of records. And to find the most recent version, I start up here and go down, or the most recent visible version, I start up there and travel down this list. That's basically how the MVCC system works. Now, to describe how PBXT itself works, this is best described by telling you exactly what the various background threads do in PBXT. And these are the 4 most important background threads. That their names make such a nice pyramid is just coincidental. I didn't actually do that by design. So, writer. What does the writer thread do? This looks a little bit complicated, but actually it's quite simple. We're starting up here with an insert or update. Delete is actually the same, but it's just this control data packet. So insert or update, though, has data to it, the fixed part and the variable part. What I didn't mention was that this fixed part is determined when a table is created. Then it uses a heuristic to decide how big this, how long the fixed length data component should be. And I'm going to show how different configurations of tables can actually be better in various situations depending on what your hardware configuration is. So what happens? The record is inserted by, first of all, writing the extended data component here to the data log. And these 2 components, the fixed length component, are written to the transaction log. At this stage, actually, the update is on disk. Those are both log files. But at the same time, it writes this control data to the record cache, which is an image of the row index and handle data file on the disk. That's why they kind of look similar here. But this is not allowed to go to disk yet. And then, if there are any indexes for this table, the index entries are created in the index cache, so they don't go to disk yet either. I've combined the 2 here, made no distinction. And the index entries point to the records themselves, not the rows, but the records. So, I mean, this pointer is sort of virtually pointing to the cache here. Obviously, it's reading the cache, so it's thinking it's reading the disk, but it's actually reading the cache, if you know what I mean. So what does the writer actually do? It simply has a job to transfer the stuff that's written in the transaction log to the disk itself in the background. And when doing this job, it can do an important optimization, which is to sort and consolidate the data that's been written to the disk, which reduces the number of IOs and also turns what you're doing here as random writes into sequential writes of the row and handle data file themselves as well. The data logs, though, are always being written sequentially, and these records are just written one after the other in the data log until the data log is full. And then it switches to a new data log, and we'll get to that when we get to the compactor thread in a minute, how that works. So what does the sweeper do? Oh, there's an important thing to note here is that the writer doesn't care about transaction boundaries. So it doesn't wait for a transaction to commit. It can just work at its own pace. If it runs out of cache, or the system runs out of cache, it just transfer the stuff to the disk. It just tries to batch it as much as it can, but it doesn't worry about the transaction boundaries. Yeah, question?
Does that mean that you can write in the background while other transactions are committing?
So the question is, can I write in the background while other transactions are committing? The answer is yes. It can write at any time, and as I said, it doesn't worry about the transaction boundaries. The thing that worries about the transaction boundaries is the sweeper thread. So what the sweeper does is it waits for a transaction to either commit or roll back, and then it follows on, it reads the transaction and what was done, the records that were affected by that transaction. And now there's a transaction log cache, so it's very likely that the sweeper is reading that data directly from the cache, not from the disk, because it's right on behind the transaction. And so we look at an example here, record X, and assuming this record was committed, what the sweeper will do is it will locate the record, and this green tick means is the action of cleaning that record, which means it writes something into the header to say this record is visible by everybody. And then it removes the older variations. Now this record is visible by everybody. You can remove the older versions of the record, and that's the deletion here. And at the same time, it removes any index entries that refer to that record. That's this deletion here. And it also marks the index entries that point to this record as visible by all. That's important for, that's a new addition actually, and it's important to be able to handle index coverage correctly. Yeah.
Does the commit operation wait for the overwriter thread to confirm the data was actually written to disk?
No, the sweeper doesn't have to wait for the data to be written to the disk. The sweeper has to wait for the log to be flushed. In other words, the transaction to be committed. That occurs when the log file here is flushed. That occurs simultaneously. Okay, either committed or rolled back, the log is flushed, and that's all the sweeper has to wait for. It doesn't have to, the sweeper is independent of the writer, if that's the question. And if this was a rolled back record, then the sweeper would just come along here and delete this record and delete that index entry, and it can do that in the background. So that's what makes the commit and the rollback in PBXT so fast, because there's nothing to do. It's all done by the sweeper in the background. So this is what the compactor thread does. The compactor thread only deals with the data logs. So there's just one detail I forgot to mention here. This, here we're deleting an extended data record as well as part of this. And what the sweeper does there is just marks that data in the data log as deleted. And now, of course, you've got a hole in the data log. And so it takes, updates in the header of the data log the amount of bytes it's deleted by this action. And so we have an accumulation. We know how many bytes of garbage we have in the data log. And what the compactor then does is it waits for the garbage threshold to reach a certain point, and this point is settable, but by default it's 50%. And when there's that much garbage, all the compactor does is it goes through the old data log, creates a new data log, copies everything that's still valid over to the new data log, and then removes the old data log when it's complete. And in doing this, it also updates the handle in the control header of the record so that the record can find its extended data. And in this way, this happens in the background, so in this way we're actually reclaiming disk space. The file system is having disk space freed up to it without actually having to do something like an optimized table. Yeah, Barry?
What impact does that have on the cache?
On the cache? What impact does that have on the cache? What do you mean, which cache?
To write the new log file, pull it into memory.
So, yeah, writing the new file means I'm pulling cache memory in. I haven't actually measured what effect that might have. Just the fact that these are both sequential operations, sequential reads, sequential writes, makes it as optimal as it could be. That's the main advantage of doing it this way.